Okay, this section 4.3 is all about curve sketching, but before we actually get into curve sketching, we're going to examine the case of rational functions, which you may recall from chapters 1 and 2. Rational function, if you look at the first 5 letters, spells ratio. It's a ratio of two polynomials. For example, if you have something like 2x minus 3 divided by x plus 1, okay, that would be a rational function. So we're going to look at what's called a vertical and horizontal asymptotes of a rational function. So we're looking at asymptotic behavior. Okay, asymptotes. So there's two types, vertical asymptote, and you have the horizontal asymptote. Okay, we abbreviate this as VA for vertical asymptote, and abbreviate that as HA for horizontal asymptote. So if you take a look at the definition 1 of a vertical asymptote, it's defined to be, it's a vertical line, so it's x equals some constant. X equals a is a vertical asymptote of a rational function of y equals f of x if the limit as x goes to a of f of x is either positive infinity or negative infinity. Okay, so if you were to look at the example I gave earlier, let's call it example 1, you have f of x equals 2x minus 3 divided by x plus 1. We're looking for the x value that when you approach that x value, the function blows up. It goes off to positive or negative infinity. Okay, so if I look at, for example, what happens when x goes to negative 1 or gets close to negative 1 of 2x minus 3 over x plus 1. To understand this better, we're going to actually look at the limit from the left and the limit from the right. Okay, if you draw a number line, you might be able to see this. It's been a while since we did limits. So let's say this is negative 1. If I approach negative 1 from the left, I'm looking at points like negative 1.01, etc. So if you look at making a table, perhaps using a calculator, you can try values like negative 1.01, negative 1.001, etc. and see what happens to y. Similarly, you can look at the right side direction. So that would be like, this is 0, you have negative 0.9, negative 0.99, negative 0.999. Let's see what happens. So let's go to y equals, and then of course, as always, you want to make sure that when you type it in, you use parentheses. So you have 2x minus 3 divided by x plus 1. And your calculator should be in the ask mode, and delete all the other stuff. So I'm going to type in the numbers from the first table. I'm going to do negative 1.01, negative 1.001, negative 1.2. Put a bunch of zeros, getting really close to negative 1. You can see the y value is getting really large. Okay, so 502, 502, 5002. So I get closer and closer to negative 1. This goes off to positive infinity. If you repeat this with values from the right side, I'm going to just type over this, negative 0.9, negative 0.09, negative 0.009, and so on. So negative 0.0, oh, I'm not getting close to negative 1. Negative, I need to have negative 0.99. So I was wondering what was wrong there, excuse me. So negative 0.99, negative 0.999, and so on, negative 0.99999. These values are getting large, so it's negative 48, negative 498, etc. Big numbers. As you get close to negative 1, this goes off to negative infinity. So this limit approaches either positive or negative infinity depending upon the direction in which you're approaching negative 1. So x equals negative 1 is a vertical asymptote. I'll show you a shorter way to compute this when we do a summary of all this, but basically you can notice that this happens when the denominator is 0. The next definition, definition 2, is that of a horizontal asymptote. Now, just how we noticed how we wrote x equals -1 as an equation. For the horizontal asymptote, it's y equals something. The horizontal line is y equals a constant. So y equals b is a horizontal asymptote of a rational function, y equals f of x, if the limit as x goes to infinity of f of x equals b, and this could be plus or minus infinity. We had seen limits like this earlier in chapter 2, where we saw long-term behavior. So this is the idea of long-term behavior. So if you use the same example that we just did, f of x equals 2x minus 3 over x plus 1, the limit as x goes to positive infinity of 2x minus 3 over x plus 1, we had learned how to evaluate these limits. As x gets really big, these numbers don't make much of a difference, so this limit is equivalent to 2x over x. We're not canceling, we're just saying that as x gets big, this is the same as this. The limits are the same. Now the x's cancel and you get 2. So y equals 2 is a horizontal asymptote. So if you were to take a look at the graph drawn on your calculator, you'll notice that on my calculator at least, it's trying to draw this, connect this end with this end. Let me do a standard window, and this is what you might notice. So the vertical asymptote is at -1, and right here the horizontal asymptote is at 2. If you actually draw y equals 2, you'll see that happening. Okay, so the way we draw this by hand is we make sure that the vertical asymptote is a dotted line always, and the horizontal asymptote is also a dotted line. Asymptotes are not part of the graph. Okay, they're imaginary lines that the graph is getting close to. So then the rest we can figure out by using pre-calc and calc, finding the intercepts and concavity and so on. So to summarize the concept of asymptotes, a little summary. To find the vertical asymptote, you first simplify by factoring and canceling, factor and reduce if needed, okay, if possible. It may not always be needed, it may already be simplified. And then you set the denominator to equal 0, and that gives you the vertical asymptotes equation. To find the horizontal asymptote, you need to calculate that limit as x goes to infinity of f of x, positive or negative, to get that. If it's a constant, then that constant gives you the horizontal asymptotes equation. For the rest of this section, we're going to be looking at curve sketching. And for this, we'll be combining concepts from pre-calc as well as calc. So the first thing you'll see for curve sketching is the concept of intercepts. To get a good graph, you need to know x and y intercept. Let's review how to find these. To find the x-intercept, I'm just going to draw a graph here. The x-intercept is right here and here and here. And at these points where it crosses the x-axis, y is 0. So to find the x-intercept, you set y to equal 0. Likewise, the y-intercept is right here, where the graph crosses the y-axis, and that's where the x value is 0. So to find the y-intercept, you set x to be 0. The next thing we need for curve sketching is to understand the domain of functions, and this is something we reviewed in chapter 2, see chapter 2. If you have polynomials, it's all real numbers, okay, with nice powers and so on. If it's rational functions, you want the denominator to not be equal to 0. If it's radicals, even radicals, you want the radicand, whatever's under the radical, you need that to be greater than or equal to 0 to avoid imaginary numbers. So for curve sketching, that's going way back into pre-calc, and then we hit the calculus topics. Namely, we figure out critical points, so critical numbers, and you may recall to do that you look to see where f prime of x is 0 or f prime of x is undefined or doesn't exist. Then the next thing in curve sketching is to look for intervals where f is increasing or decreasing. Okay, and that we use the first derivative again. Also relative max and min, and we saw this in chapter 4 earlier. We can use the first derivative test or the second derivative test. And concavity, we saw this in 4.2. Okay, that's when we look for f double prime. If f double prime is positive, it's curving up. If f double prime is negative, it's curving down. And that led into the point of inflection. That's when f double prime of x is 0 or f prime does not exist, and concavity changes. Concavity change. So using all of these facts, we're going to be able to get a perfect graph of any function. Just run through all the steps and figure it out. Okay, so one more time. Pre-calc, pre-calc, pre-calc. Chapter 2, 4.1a, critical numbers. 4.1a again. 4.1b as well as 4.2b, you can use the first or the second derivative test. Concavity is 4.2a, and that's 4.2a. So summarizing it all. Alright, let's stop here for the lecture part and go to the worksheet and try some examples and put everything together. So page 1 of the worksheet should look kind of like this. We were first finding vertical and horizontal asymptotes, and I'm asking you to write the asymptotes using proper notation. So to find the vertical asymptote, you set the denominator to equal 0. In this case, that's x squared minus 36 equals 0. You can solve this. X squared equals 36 square root, but don't forget it's plus or minus square root. So you have two vertical asymptotes. So if you want to have a mental picture of what's happening, this is 6, dotted line there, dotted line there so far. As far as the horizontal asymptote goes, we're looking to see what happens when x gets large, and if the degree of the top, degree is 2, the degree of bottom is also 2. If they're the same, then as x gets really big, you're looking at the leading coefficients. In other words, as x gets big, you can ignore these small terms and only focus on 3x squared over x squared, which reduces to 3. So the horizontal asymptote is y equals 3. Okay, so don't forget that to find the vertical asymptotes, it's x equals some number. Horizontal, it's y equals some number. Okay, these are equations of lines. So horizontal asymptote of this is 3, looks kind of like that. And then if we were to do the complete graph, we'd need to know what the intercepts are and so on, and figure out if this is what it looks like, okay, sample points, etc., etc. We'll get to that later. Alright, part B, vertical asymptote. Now if you want to pause the video and try the question on your own, and then continue and check your work against mine, that would be a good way of learning it. So if you did just pause the video, welcome back. To find the vertical asymptote, you're setting the bottom to equal 0, and that gives you x is equal to negative 11/3. That's your vertical asymptote. For the horizontal asymptote, it's the limit as x goes to infinity of 2x over 3x plus 11. As x gets big, this is not of much consequence. That 11 can go away, and you get 2/3. So y equals 2/3 is the horizontal asymptote. Last problem, for the vertical asymptote, if you set the bottom to be 0, you don't get a real solution, because when you try to take square roots here, it's an imaginary value, so this is not real, which means there are no vertical asymptotes. The horizontal asymptote, when you find the limit as x goes to infinity of 5x squared over x squared plus 1, you should get 5. So y equals 5 is the horizontal asymptote. Let's take a look at this graph. It looks interesting with no vertical asymptote. So 5x squared on the top, divided by, in parentheses, x squared plus 1. So it's not going off to positive or negative infinity, but it is leveling off over there at 5. Alright, one more page. Here's where we do a summary of all curve sketching here. And in the notes we saw how to find the x and y intercept, so let's get started. So in part A, to find the x-intercept, you let y be 0. This is y. X cubed minus 2x squared equals 0. So it says obtain as much information as possible on this function and use this information to graph. Be sure to label the important points. So for the x-intercept, this is what we've done so far. Take out an x squared, you have x minus 2 equals 0. If you set each of these factors to 0, you get x is 0 and 2, but the way we write our intercepts as ordered pairs, 0, 0, and 2, 0. To find the y-intercept, you let x be 0, so you go back here, plug in 0, this is your y equals all this, so it's 0 cubed minus 2 times 0 squared, you get 0, which shouldn't surprise you, because if the origin was the x-intercept, it's also the y-intercept. So we're done with part A. Part B, we need the domain. Now this is a polynomial. Domain is all the x values. You can plug in anything you want for x because there's no stuff in the denominator to cause any issues. There's no square roots. So you would say for this that f of x is a polynomial, which implies the domain is all real numbers. Or you can use the interval from negative to positive infinity. Domain is done. Now we're moving on to calc. Critical numbers, we need f prime of x. The first derivative is 3x squared minus 4x, and then we set this to equal 0, but I prefer factoring first, so it's 3x minus 4 equals 0, which means x is 0, comma 4/3. Those are the two critical points. For part D, we need the open intervals on which the function is increasing and decreasing. I'm going to draw a number line for part D right here. 4/3 is somewhere here, 0 somewhere here. So let's say we pick -1, 1, and 2 and plug them in as sample points into f prime. So f prime at -1, f prime at 1, and f prime at 2. Plug in -1 here and here. So negative times a negative is positive. Plug in 1 and you get positive and negative, so it's negative. Plug in 2, it's all positive. So the function is increasing, then it's decreasing, and then it's increasing again. So writing it as an interval, you would say f is increasing on the interval from negative infinity to 0, comma, or union, 4/3 to infinity. F is decreasing on the interval from 0 to 4/3. Now, that's part D. Part E is actually follow-up from this part where it says use the relative extrema. You use the first derivative test, which states that if your function is going up and going back down, you have a max there. So I'm going to simply write from the first derivative test, I have a relative maximum at 0, comma, I need the y value, and the y value is obtained from here, which is just 0. And then the function is going down and back up, so right there, that critical point, we have a relative min. So relative min is at 4/3, comma, and then we need the y value. So we plug in 4/3 into the original function. What do we get? So it's going to be, I'm going to go here. So it's 4/3 cubed. 4/3 cubed minus 2 times 4/3 squared. And let's do a math fraction. That's -32 over 27, which it's good to have an approximate value for graphing purposes. So it's -1.185 repeating. Okay, but exact values are what you're going to be expected to put into WebAssign. So this is good to know for graphing. So that's part E. Now we're going to do part F. In part F, we need to find intervals where it's concave up and concave down. Concavity, you need second derivative. Okay, so let's do that. F double prime of x, take the second derivative here, you get 6x minus 4. You set this to equal 0 and you solve, you get x to be 4/6, which reduces to 2/3. So you draw a number line again. 2/3 is right here, let's say 0 and 1 on either side. F double prime at 0, F double prime at 1, plug it in here. If I plug in 0, I get negative, so it's concave down. If I plug in 1, 6 minus 1, 4 is 2, positive. So the way we write it is as F is concave down, I'm going from left to right, on negative infinity to 2/3. F is concave up on the interval from 2/3 to infinity, which gives us, oops, here we go. So this is the work we did. Sorry, my camera was off. There's the concavity part. And then part G is find all the points of inflection. Inflection occurs where concavity changes, and that happens at 2/3. So point of inflection is at 2/3, comma. I need F at 2/3. So I need to go calculate that. It's 2/3 cubed minus 2 times 2/3 squared. I'm just going back to this to find the y value. Right here, the y value. Okay, so feel free to use your calculators right at this point. This is a squared. And see what you get. If I do it real quick here, it's 2